Hello everyone, welcome back to my Salome tutorial. In this tutorial, we are going to solve a dynamic analysis of a cantilever beam. In dynamic analysis, there are multiple analyses are there. In this tutorial, we are going to do modal analysis to find the natural frequencies of the system. So, as I have taken as steel, Young's modulus and Poisson ratio to calculate this mass matrix, we need one more property, that is called density. Density I have taken, so (7860 kg per meter cube). So now move on to the next slide. Here I have created a simple model, but actually I am going to model a 3D object, not the 1D object. So I am going to create a 3D element, then I will solve it. So here I am going to fix it, and the total length of the beam is 1 meter and cross sectional area is 0.1 meter and 0.1 meter. So this hand calculation I have made it. So for fixed and free end cantilever beam, so this is the formula we have used to calculate the natural frequencies. So from Harris Shock and Vibration Handbook 5th edition 2002, I have taken formulas. As we have seen, we have taken a steel with the 210 gigapascal, density 7860, and width and depth of the beam we have taken 0.1. So length of the beam we have taken 1. So first moment of inertia, when for I1 and I2 we have taken same value we are getting, because we have a length and breadth, breadth and depth are same, 0.1. So mass per unit length of the beam is 78.6. From that, some natural frequencies we have calculated, so these values. So by writing in ascending order, so 83.5931, 83.5931, then 522.457, 522.457. Similarly, I have written in ascending order. So this is the natural frequencies we have calculated from the formula. This is hand calculation we have made it. Then we'll do finite element analysis using Salome software. Then we'll check the results from that software. First, I'm opening the software. So modal analysis is the one of the very important analysis in dynamic analysis. If you go for any model to check for frequencies, we used to do modal analysis. So if the natural frequencies matches with the excitation frequency, the system will vibrate and fail. So for that we need to know the natural frequencies of the system. For that we need to do modal analysis. So now the Salome software is got opened. Now before going into the software, just go into File, Preferences. Now we are in General. So first we'll finish modeling. Just go to Geometry. Now we just see the model. So our model having a length of 1 meter and cross sectional breadth and depth are 0.1 and 0.1. So we'll model this one in Salome. So we can directly go into cube. So new entity, basics, Here there is one more option, is called primitives. Just move into the primitives and box. So in x direction length is 1 meter, y and z both are in 0.1. To preview, just move this pop-up window in your left side and go to fit screen. So this is the model we are going to take. In this particular tutorial, we are going to take a 3D element. In next tutorial, we'll take a beam element to solve the same case, and we'll compare the results what we are getting. So now we have modeled this beam element, 3D object, then apply and close. Now we have created this box here. Then we just want to create groups for applying the boundary condition. Now just go to the model. In left side we are going to fix it. For that we need to create a groups, face group, to apply the constraints. Now right click here, go to create group. Now select this shape type as face and select the surface, add it here. Now this surface value is added here. This 3 is this surface number. Every surface having particular number, that number will get added here. So now just apply and close. Now just apply it. Now see, we have created this group. Now you can close it. Now just rename it as fix. Now just I have renamed as fix because I am going to fix it here. So now you just save this file, go to file, save as. Now I am saving it in pictures, aster 12. So I have already one file here, that's why I am saving it as study 2. So I have saved it here. Now just go to mesh model. Now we have created the geometry. Then we need to create a mesh or finite element model for analyzing. So select this box, go to mesh, create mesh. So now we have 3D geometry. Now we will create a hexa element. So go to hexahedron. In 2D you just make it quadrangle mapping. So these are algorithms to generate the mesh. 1D will use wire discretization and we'll go for local length. There are different algorithms are there, we can use it. Now I'm going to use local length 0.02 I will take, then OK and apply and close. Now just right click this mesh one, make sure that you have selected this mesh one, right click it and compute. So it will generate the mesh and it will show the information of the mesh. Now you can see it. So our mesh having 240 edges and 1050 quad elements. You can see it, tria elements, quadrangles and polygons. Now we have 1050 quad elements at the surface and 1250 hexahedron element. So there are different elements we can generate: tetra, hexa, pyramid, prism, hexagonal prism, polyhedrons. Now we have only 1250 hexa elements. This is our mesh information, and these elements are in linear type. Okay, so we later we will see how to use linear, quadratic and biquadratic elements. Okay, now just close this. Now we have created the mesh. So this is the group we are going to apply constraints. So that also taken into the mesh. Now I just saving this file. Now just move into aster study. As you have seen, we have created the geometry and we have created the mesh. Then we need to apply the boundary conditions and material property and type of study, everything we need to specify it in code aster. So use aster study. So it will ask which version you want to use for solving. I want to use stable version. Just give OK. Now we are in code aster module. So before going into it, you just go to file preference, because Codaster is developed in French. It has a translation. To make it default translation, make sure you have use business oriented translation, and here documentation you just make it English. Okay, these two things you just make it. One is use business oriented translation and use language English. Then you just apply it, make it okay. Now we have changed that into translation. We are using translation. Now we want to add modal analysis. So two way we can do it. We can do one by one. You can see here, one by one we can add and we can do the analysis. Another way is we can use assistants. You can see add a stage, one by one we can add. Otherwise we can go for assistant to do the modal analysis. So now I'm going to use assistant to solve the modal analysis. So just go for modal analysis. Here you can see only block displacement it will do, 2D and 3D mesh only it will do. It has a limitations. This assistant having limitations, but by using this we can do any analysis. So go to next. So mesh 1 it has taken from the mesh module, and go to next. This is a 3D. We can do plane stress, plane strain and axis metric here. So now our model is 3D model. So choose 3D, go to next. So Young's model is and 210 gigapascal. Density here they have mentioned 7800, but we have mentioned 7860.3. Go to next. Now we just want to fix it as, so impose the degree of freedom on groups. Go to fix, select this one and just fix it, because solid element have every node having only 3 degree of freedom, that is 3 translation degree of freedom. So we need not to specify rotational degree of freedom, so only translation degree of freedom is enough. So I'm just fixing this fixed group as 0. Go to next. Now we can specify how we can generate the frequencies. We can specify by number of eigenmodes, or we can specify by band. For example, 100 to 500 in between, whatever the natural frequency is that has to be calculated. That way we can specify the frequencies that we can specify. Now I just want to specify number of frequencies. I just want to see 15 number of natural frequency. It will calculate from 0 to 50. One by one it will calculate. First natural frequency, second, third, fourth, fifth, like that it will calculate. So I want to see 15 number of natural frequencies. So go to next. Now I just want to save the results file. Go to browse, pictures, Codaster. Here result modal.rmd. RMD is file format. So save it. Finish. Here we can see one by one how it has generated. Now you can see first we need to read the mesh. Next we need to define the model. What type of model is ours? Is a 3D model, a 2D model, axis metric, that has to be defined here. Then we need to define the material. Then we need to assign the material to the model. Then boundary conditions. We have fixed the boundary condition. Then assemblage. What it will do is it will calculate the rigid matrix and mass matrix and it will assemble. Then calc modes. It will calculate the modes. This is the analysis type. So calc mode is the solver we have taken. So then finally output. So output is, it will save the output in MED format. Here you can see. Now we have done so our setup. Now we can go for solving. Go to history. Select this current case. First press this run. Then click this one. It will save the results. Then you just go here. Change this into auto references 5 seconds. Here we can we can change this one. Case type, memory, how much memory you want to use. If you have a very big system with more RAM, processor, everything, you can specify it here. And time you can also specify here. 15 minutes is more for this simple case, so I'm just specifying 15 minutes. Then the code asset version is 15.6. now you can go for run. So there is a gear button, you can see here. Just click this gear button. You can see here the case is running here. Now you can see the green color button with the tick it comes. It means that there is no error in solving. So here also you can see this is a message file. So our diagnostic job okay. That means there is no error. It has solved nicely and saved in same locations. Now we can go for paraview to view the results. So now and message file also we can see what are the frequencies it has calculated. So these are the command it has run. So these are the frequencies. See, this is a serial number frequency. So first frequency is 84 and second frequency is 84. So third and fourth frequency are 505. Fifth frequency is 749 and sixth frequency is 1296. So like that it has coming frequencies. The first fundamental frequency is 84. Okay, now we'll see the result in which direction it's getting deformation or which direction it's bending. Like, so two things we need to see. One is what is the frequency value, and next one is in which direction it's deforming. So now we'll see in paraview. Just go to paraviews. Paraviews is the one of the wonderful post-processing tool for Codaster and which is open source also. Now just click this built-in, go open Vengat pictures Codaster. So our result file is result_modal.rmd. Just select this file, give OK, give apply. So now this is our geometry. Now go to displacement, change this into blue to red and apply this value as 12. To see the direction of displacement, you just go for wrap by vector to see the deformation. So apply 50%, not the full one, then apply it. So the first mode you can see which is bending in y direction. So the frequency of the first mode is 84.25. Similarly, the number of frequencies it has calculated one by one we can see. The first mode it is bending in y direction. Similarly, the second mode, which is bending in z direction, you see, which is bending in z direction. And third mode, which is bending in y direction with the one node. Here they will say with one node. Then this is bending in same z direction. Fifth mode is the torsional mode. See, it is twisting. Fifth mode is the torsional mode. You can see this is twisting. And sixth mode is the tensile mode, which is elongating, which is coming in this direction. These are multiple mode. We'll see one by one. So this is the sixth mode, which is tensile mode. It's extending and compressing it. So which is sixth mode is so rigid in that. So the frequency is coming around 1296. Seventh mode is a two node, one node and two node. Two node it's actually bending. 8th mode also it's a tensile mode, sorry, 8th mode also bending. 9th mode is a twisting mode with one node. There are two positions here and here, it's getting twisting. So like that we need to check it, and we need to check with the external frequencies. So in this tutorial we have compared the calculated results. So now you see the results. So this is the calculated value. 83.8 is coming in calculation, and in finite element analysis we are getting around 84, which is very close. Similarly, second mode also 84. Third mode is coming around 505. Here you can check the third mode is coming 520. Little changes. Like this we can compare the results. So to making mesh finer and finer, we can make the results closer to the calculated value. So in that we have finished our tutorial. So next tutorial we'll do the same problem using beam element. So thank you for watching my videos. Please subscribe my channel for more videos, and please click the bell button to get the notification while uploading videos. Thank you.